The goal of this video is to use the supermagic formula to calculate the acceleration of a point P on a two-link robot arm. You should remember the two-link robot arm from our homework, but I'll draw it out, of course, just in case. So here we have our first link, and that link can rotate about one of its ends, and the point at which it can rotate is point O. Then we have a second link, which also can rotate, and so the point at which it rotates is about the end of the first link. And we called that rotation point R. And then the point that we're trying to calculate the acceleration of is located at the end of the second link here, and we call that point P. So we start by defining our reference frames, and we're going to use that to get the position vector and the ROP, and then we'll go through the whole process. So our fixed frame is frame A. I'm going to draw that right here such that its origin is at point O. We then introduce a second frame, which is going to capture the rotation of link 1. So it makes sense to draw that frame as such. So this is B1, we have B2. Right, so the direction of B1 is in the same direction as this vector here, R, O, R. And then we draw a second moving reference frame here, which will be C, frame C. So we have C1, C2. Again, you see that I've drawn that C1 unit vector in the direction of this position vector here, which is R, RP. And again, we have a total of 3 reference frames for this system. That's because we have one fixed frame, and then we have 2 moving bodies, 2 rotating bodies. So each of those rotating bodies has its own reference frame. So now we move into actually defining the position of point P. So the position vector that we're looking for is our OP. Our OP is equal to R OR plus R RP. And R OR, as shown here, is defined in frame B. I should also note here that the length of link 1 is L1, and the length of L2 is L2. Okay, so we have the position vector ROR, again in frame B, is equal to L1 B1. And the position vector RP is defined in frame C, and that is L2 C1. And just as a reminder, I'll put here that this is frame C. Let's switch the colors. Frame B and frame C. So using this information here, we're now going to move forward in calculating the acceleration using the supermagic formula. in the last problem, when we used the supermagic formula, we only had one rotating frame. So we had a fixed frame A and frame B rotated with respect to frame A. Here we have two rotating frames. We have frame B and frame C. And so when we have two rotating frames, we write the supermagic formula as follows. So we have the acceleration of point A in point P in frame A, excuse me, is equal to the acceleration of point R in frame A plus the acceleration of point P in frame C plus 2 times the angular velocity of frame C in frame A crossed with the velocity of point P in frame C plus the angular acceleration of frame C in frame A crossed with our position vector RP plus the angular velocity of frame C in frame A crossed with, again, the angular velocity, which is crossed with our position vector here. So again, this is our supermagic formula. Super magic formula compared to the last example, right, where you saw C's, you saw B's, right? So here, because again we have two rotating reference frames, our last position vector that is pointing to point P is R of P, and R of P is defined in frame C. Hence, these terms are looking or comparing frame C with respect to frame A. And if this is confusing at all, of course, you can just write down in your notes and just remember, typically we only deal with one or two rotating reference frames. But you can imagine how this extrapolates up if you had three rotating reference frames. Now we're going to dive in and calculate each of the terms of our supermagic formula. And we're going to start with what is perhaps the hardest or longest term here. So here we have the acceleration of point R in frame A. But if you look at our position vector up here, you will see that we have the position of point R, so that position vector OR, we have it written in frame B, not in frame A. So what that means is to calculate this acceleration of point R in frame A, we actually have to use the supermagic formula. So now we have to basically write this out. So again, we have the acceleration of point R in frame A. And we write this out knowing that, again, point R is defined in frame B. Okay, so how do we use the supermagic formula in this case? Well, we now have the acceleration of point O in frame A, plus we have the acceleration of our point R in frame B, plus 2 times the angular velocity of frame B in frame A crossed with the velocity of point R in frame B, plus the angular acceleration of frame B in frame A crossed with our position vector ROR, plus the angular velocity of frame B and frame A crossed with, again, that angular velocity, which is crossed with our position vector, RRP. Now let's go through these terms, right? Feels very meta here. So the acceleration of point O in frame A, so again, O is this origin here, O is not moving. Therefore, that term is equal to 0. Next, we have the acceleration of point R in frame B. So for that, we pop up here and we look at this position vector. And we see that the position vector is defined as L1, B1. L1 is static, right? So L1 isn't changing. So that acceleration is also 0. Now we have our angular velocity of frame B and frame A, which is defined as theta dot B3. And that's crossed with the velocity of point R in frame B, which again, coming back up to this position vector here, you take the derivative of this, and that is actually 0. Now we have the angular acceleration of frame B and frame A, which is the derivative of the angular velocity. So that is going to be theta double dot B3 crossed with ROR, which we have defined up there as L1, B1. And again, we have our angular velocity, so that's theta dot B3 crossed with theta dot B3 crossed with our position vector L1, B1. So while it may have looked intimidated to take a supermagic formula in a supermagic formula, you can see here that actually a lot of the terms cancel out, right? So that these all go away. And what you're left with is the following. We have our, starting with this term here, this cross product is L1 theta double dot. B3 crossed with B1 is B2. And I should also quickly just go back and define these are theta 1s, right? Because theta 1 is this rotation here, and theta 2 is this rotation. Right, so just to say that again, theta 1 is the rotation of frame B with respect to frame A, and theta 2 is the rotation of frame C with respect to frame A. So just before I forget, always important, label your thetas. Okay, so getting back to this, so we have this first term here is equal to this term here. Now we need to take, we have plus theta dot 1 B3, and this cross product in this parentheses is equal to L1 theta dot 1 B2. So now we take that cross product, so we're left with L1 theta double dot, theta 1 double dot B2 plus, so we multiply these terms out, so we get L1 theta dot 1 squared, and the cross product between B3 and B2 is actually negative, is negative B1, right? And so now we have our acceleration of point R in frame A, and we plug this back in here. So I'm just going to quickly wipe this screen, and now that we've calculated this AAR turn, just so we have a little bit more space. Now that our rearrangement is complete, we're going to go back to our original super magic formula, the one that we're using to calculate the acceleration of point P in frame A. So we just finished the arduous task of calculating this term, which again we needed the super magic formula for, so that was the acceleration of point R in frame A. It turned out to be not as bad as we thought, and ultimately we found that this term was equal to L1 theta double dot 1 B2 minus L1 theta 1 dot squared B1. Next we have this term here, which is the acceleration of point P in frame C. So for that we come over to our position vector here, which defines the position of point P in frame C. Now, to get the acceleration, we take the double derivative of this position vector. Because L2 doesn't change, again it's static, this acceleration term turns out to be 0. The next term here is 2, and then omega c, so our angular velocity of frame C with respect to frame A is equal to theta 2 dot C3. And we're going to cross that with the velocity of point P in frame C, which again, that brings us back to this position vector here. If you take the derivative of this position vector, again, L2 doesn't change, so that turns out to be 0. Then we move to this term. So here we have our angular acceleration of frame C and frame A, which is just the derivative of our angular velocity of frame C and frame A. So this can be written as theta 2 double dot C3, and we cross that with our position vector as written here. So that's L2 C1. And lastly, we have this term here. So I'm just going to write that down here for a little bit more room. So our angular velocity of frame C and frame A is theta 2 dot C3, and that's crossed with, again, that angular velocity, which is crossed with our position vector, which is L2 C1. And now it's just a matter of going through and calculating the cross products and canceling things out. So to simplify, we have our terms here. So L1 theta 1 double dot B2 minus L1 theta 1 dot squared B1. This 0 goes away. This cross product with 0 goes away. Now we have L2 theta 2 double dot, and we have the cross product between C3 and C1, which is C2, plus have theta 2 dot C3 crossed, and we'll take this inner cross product. So we have L2 theta 2 dot, and again the cross product between C3 and C1 is C2. Now we just write this all out again. and we take this cross product here, and so that's going to give us L2 theta 2 dot squared, and the cross product between C3 and C2 is equal to negative C1. So if you were to check that with your acceleration with your homework solutions, you would see that they are identical. So this here is an example of using the Supermagic formula when you have more than one rotating frame. Right? So ultimately we had to actually use the Supermagic formula twice. It sounds terrible, but turned out it's not as bad because at least in this example, terms canceled out. Of course, that's not always the case. The more complicated the problem, the longer the equations. But again, as long as you have the Supermagic formula and you can calculate each of the terms in that formula, you will be all set.